Welcome back. We're talking about extension complexity, and in particular, this is our second lecture showing a result that says that the extension complexity of the correlation polytope is exponential. It's at least 1.5 to the n. Let's recap very briefly what our roadmap is, where we are and where we're going. Now recall from previous lectures that the key idea is to use communication complexity, in particular non-deterministic communication complexity, for this game, this face vertex game that Bob and Alice will play. Namely, that means that they want to evaluate this face vertex function, which takes a face and a vertex and outputs 1 if the vertex is not in F, and 0 otherwise. And note that this is entirely given by the slack matrix. The slack matrix encodes F, V. And in particular, the support of the slack matrix, where it has zeros and non-zeros, encodes V. So let me add that. The support of the slack matrix encodes FV. So let's remember what this slack matrix is, or actually, I will just write the support of the slack matrix. This is a very large matrix where its columns correspond to vertices. And recall that the vertices of the correlation polytope can be identified with subsets of 0, 1 to the n. So this is chi b transpose, the outer product of the indicator or incidence vector of a subset B of 1 to n. And rows correspond to all of the facets. Now, we're going to make this problem simpler because we're interested in a lower bound. So Alice and Bob are each going to get a row and a column, respectively, of the support. And ideally, their goal is to be able to agree, given the hint of the prover, or the proof of the prover, on whether or not they have a 1 in that FV point. We're going to make this problem easier by only looking at a subset of S. So we're only going to look at the subset of rows, and these facets are going to be only those special facets we defined in the previous lecture. And recall that those special facets, there are exactly 2 to the n of them. We can identify them also with subsets of 0, 1 to the n. So we're going to call these F A. And this is especially convenient because we have A for Alice, B for Bob. And that means that from now on, as mentioned at the end of the last lecture, we're not going to be talking about FV of little f, little v, but rather FV of A, B, since for any subset A of 1 to n, we can identify that with one of those special facets, FA, and for any subset B of 1 to n, again, I associate that with the vertex YB. Okay, so now we have an easier problem. We're just working with this subset of the support of the matrix that's the support matrix of S. We're going to make this further easier. And what we're going to do, we're going to make this easier still. We're going to essentially make an agreement. Alice and Bob are going to be given side information ahead of time, and they're going to be told that their A and B are going to have intersection either 0 or 1. So again, because of the special properties of Fa, Fa, now you'll have to look back at the last lecture to remind yourself of this. We know that that YB is an element of Fa if and only if A and B have intersection 1, which is equivalent to saying that FV of AB, in other words, every entry of this restricted matrix, is equal to 1 if and only if A intersect B is not equal to 1, which means that the intersection of A and B could have cardinality 0 or 2, 3, 4, something bigger. So we're going to make this easier by promising Alice and Bob that we are only going to give them A's and B's that have intersection either 0 or 1. So the task, as I wrote it here, would be for Alice and Bob to jointly determine whether there A and B have intersection different from 1. In other words, but we're going to make this easier by we give side information that A and B is only going to be either 0 or 1. Another way to say it, and the way that I phrased it at the end of the last lecture, is that we change our protocol and we declare victory that Alice and Bob win if whenever A and B have intersection 2 or more. So this is they only need to resolve whether A and B has intersection 0 or 1. So in other words, we're basically the slack matrix has 1s and 0s. And Bob and Alice are only playing the game where they need to determine whether it's one of the where it's one of the ones that corresponds to A and B having 0 intersection, because there are also ones that correspond to A and B having intersection 2 or having intersection 3. And so we have made the game even easier. So we're going to define exactly what these ones are, and we're going to talk about how this relates to covering and communication complexity. So we're going to let D of n be all of the ones that Alice and Bob are responsible for getting correctly, all of the ones in that restricted portion of the support of the slack matrix. So in other words, remember this, in the restricted portion we said is indexed by subsets A and B. And so the ones that Alice and Bob are responsible for are indexed by those A's and B's. Again, these are each subsets, such that A and B have intersection of cardinality 0. In other words, their intersection is empty. Now, recall from our first lecture on communication complexity that if the slack matrix, the support of the slack matrix, or really this face vertex matrix, had blocks, then the hint could just be which block are they in. We are going to try to do something similar. We're going to try to cover D of n with some certain number of sets. They're not going to have to be blocks, but keeping this in mind will help give us intuition as to why we make this restriction. So let's start with this important definition of a valid set. And in this example, a set would be valid if it were a rectangle, but we're not quite going to have that. But it will be, as you'll see, very related. So a subset of these critical ones that we need to determine is called valid if it has this following property. If for any two pairs, AB and some other pair, A prime, B prime, both of these belonging to R. So for any two pairs, AB and A prime, B prime of R, then A and B prime is not equal to 1. So let's again understand what that means. And also, since this has to hold for any two pairs, this also implies that A prime and B is not equal to 1. Okay, so again, let's see what this means. It's saying that A and B, if they're going to be in R, they're going to be in D. So they have empty intersection. So we know that A and B and A prime and B prime, each of them independently, have empty intersection. For them to be in a valid, so a collection of those is called valid if it has this particular property. Now let's get some intuition about why this is useful and how does this relate to communication complexity, and how does this relate in particular to this intuition that we had initially when we talked about non-deterministic complexity in the blocks. And so what I'll just say about this here is that because of this definition of valid, it allows us to directly map directly link the cardinality of a covering of D of n with valid sets to an upper bound on the communication complexity, the non-deterministic communication complexity. So let me explain. Again, you should keep in mind our example with covering the matrix of FV with blocks. So suppose we have a covering of D of n with R valid sets. So in other words, D of n is contained, and actually it would be a quality since a valid set is a subset of D of n. R1, R2, R little r, where each Ri is valid. So let's see how we can define a communication protocol that will allow Alice and Bob to win the game. So what does the prover do? Okay, so first in our game, Alice receives A, Bob receives B, and the prover sees both A and B. And recall, by prior agreement, the intersection of A and B is either 0 or it is 1, but it can't be more than that. And all we are interested in is if A and B have intersection 0, in which case FV of AB would equal 1, we need to get Bob and Alice to accept the proof. So what happens? If A and B have intersection 0, in other words, if FV of AB equals 1, by agreement, this can only happen if the intersection is empty. Then A intersect B is empty. Remember, larger intersections are not allowed by our simplification of the game. And in particular, that implies that A comma B is in our set D of n. And therefore, A and B is in one of these Ri's. Let's say it's in Ri. So what does the prover do? The prover sends to Bob and Alice this index I. So prover sends or publishes this index I to Alice and Bob. And note that Bob and Alice can now individually check. So Alice checks. Alice has A. So Alice checks whether A, her row of the matrix, corresponds to some element of the cover, the same way that Alice would check if her row is an element of corresponds to one of these blocks. So how does Alice do that? Alice checks if there exists some other B, let's call it B tilde, such that her A with B tilde is an Ri. And if so, Alice accepts the proof. And similarly, Bob checks if there exists some other A such that A tilde with his B is in Ri, and if so, Bob accepts. Now, did they succeed? Since they both accepted, that means that they both believe that the intersection of A and B has to be 0, cannot be 1. And indeed, we can see that that's the case. And that's exactly why we need validity. So if Ri is valid, that means that if A and B tilde is in Ri, and if A tilde and B is in Ri, well, looking at the condition of validity, this means that A and B does not have intersection 1, which means, based on our simplification, that it has to have intersection 0, and hence Alice and Bob win. Okay, so this provides an intuition of where this definition of validity comes from, and how it connects to communication complexity. But of course, this argument gives a bound in the other direction. Right? So this is saying that if we have a covering, that's an upper bound on the communication complexity, which what we really want is to show that any extension complexity, in other words, any extended formulation that has R facets is going to be an upper bound on the covering that we need. And then we're going to show that we cannot have that there is going to be no small covering. This is how we're going to proceed. Okay, so what we really want in our critical lemma is the following. It's going to tell us that if we have an extended formulation, if Q is an extended formulation for the correlation polytope with R facets, in other words, i.e., there exists an affine map pi, so that pi of Q is equal to our correlation polytope, then there exists a covering of D of n of size R, the number of facets. So the size of an extended formulation is upper bounds the size of the smallest covering. Therefore, if we can show that the smallest covering is very large, that means that the size of the best extended formulation, in other words, the extension complexity, is also going to be at least that big. So this lemma is important, and this gives us exactly the link that we need. And in the next lecture, so we're going to prove this in this lecture, and then in the next lecture we're going to prove a lower bound on how big a covering could be. So again, the remaining two proofs is prove this lemma. That's this lecture. And step 2 is to show any covering has at least 1.5 to the n requires sets. And we're always going to be focused on valid sets. Let me make sure I define that. So I defined what valid means. I guess I didn't define what a covering. So this a set is a covering if not only does it contain d of n, but they are all valid. So when I wrote here that Ri is valid, this is actually a definition of covering. And therefore this lemma is saying that there exists a covering of dn that implies with valid sets. Or again, valid is the definition we gave on the previous slide. So the proof of this lemma is going to feel very familiar to us because it looks very similar to the second proof of how communication complexity lower bounds this the extension complexity. It's going to look very, very similar to that, and we saw that in a previous lecture. So let's get to it. So Q is our extended formulation. And pi is our affine map. Pi of Q equals the correlation polytope. I'm dropping the n superscript n notation. And Q has facets G1 to GR. I'm going to use these facets to define valid sets. Use these. So we use these to define valid sets, Ri, and then we show that these form a covering. Okay, so this is the idea. So for any facet G of Q, the extended formulation, define the set R sub G is all pairs AB that are disjoint, in other words, that are the ones that we want to cover. Remember, we're going to build a covering here. This is our valid covering. Such that two properties hold. Property 1 is that pi inverse of the face that corresponds to A, remember FA is that special face that we defined in a previous lecture, is contained in G. And the second property is that pi inverse of the extreme point corresponding to the subset B, its inverse image in the extended formulation Q, is not contained in G. Remember that both that FA is a face and YB is a face, a vertex is also a face. And so under the affine transformation pi, the inverse image in Q will also be faces. So what we're saying now is that that RG is the set of pairs A and B, so that the inverse image of the vertex, that face in Q, is not fully contained in the inverse image of the face FA. These are all the sets FA that we're looking at. Again, I encourage you to look back at the proof we gave, the second proof of communication complexity, lower bounding extension complexity, and you'll see exactly these two properties, which is really the motivation for during that proof for me writing those properties in this slightly more general way than we needed it there. So there's two things we need to show. First, we need to show that RG defined in this way is valid. And secondly, that the union of RG1, RG2, etc. up to RGR form a covering of D of N. And that will conclude what we want to prove. So let me write that down. We need to prove two things. Claim 1, that RG is valid, defined in this way. And claim 2, that they form a covering. In other words, D of N is contained in the union of RGI. So let's prove claim 1. Proof of validity. What do we need to show? Well, this is pretty straightforward, right? We need to show that the definition that if AB and A prime B prime is in RG, then I need to show that A intersect B prime is does not have intersection 1, is not equal to 1, and similarly, this would also imply that A prime intersect B doesn't have cardinality 1. Now let's suppose it does. For if A intersect B prime equals 1, what does that mean? Remember, this is the magic of our special faces that we're looking at, FA. A vertex is in FA if and only if the two sets that define them respectively have intersection 1. So in other words, this is exactly equivalent to writing that the vertex corresponding to B dash, is in FA. But what does that mean? If this is so this certainly implies that the inverse image of YB prime in Q. I'm intersecting with Q because pi is an affine map. So all of the points of Q that map onto YB, if YB is in FA, will certainly be contained in pi inverse of FA. But this pi inverse of FA, by definition of property 1, is contained in G. But that means that pi inverse YB prime is contained in G, and that violates property 2. So this would therefore be violating property 2. So that does it. That does it for that. So let's now prove claim 2. Proof of claim 2, union of these valid sets is a covering of D of N. So indeed, let's take any element of D of N, and we need to find that it's in one of these RGs. So let's take A hat, B hat in D of N. So recall that so far all this tells us is that these have empty intersection. And now let's look at the face that's defined by A hat. And so this is a face of the correlation polytope. And I can look at the inverse image of this face in Q, and note that as we've mentioned in a previous lecture, and as I marked it as an exercise for you to show, and I encourage you to do that here if you didn't do that a few lectures ago, show that the inverse image of a face is again going to be a face. So this is a face of Q. So again, to be clear, what that means is if I look at the inverse image of, say, an entire face or a lower dimensional face, it's not going to map to something that's like going through the middle of the polytope. Geometrically, that's what that statement is saying. Now, what is the other property? Again, we use this in the previous proof that I keep referring to. We know this fundamental property of polytopes that tells us that any face is exactly equal to the intersection of the facets that contain it. So, in other words, since any face of a polytope is the intersection of the facets that contain it, this guarantees that this pi inverse of FA hat, this face, is exactly equal to some intersection of those facets of Q. So it's the intersection of GI1 and GI2 and some other ones, GIK. Now, we know, meanwhile, that since A and B do not have intersection 1, in particular they have empty intersection, this implies that this extreme point is not an element of this face. There's a lot of notation, so perhaps I repeat myself a lot on this. Remember that the faces are defined so that an extreme point YB belongs to face FA if and only if A and B have intersection 1 element exactly. In this case, A hat, B hat have no intersection, therefore YB hat is not an element of FA hat. And therefore, that means that pi inverse of YB hat, that this cannot be fully contained in pi inverse of FA hat. And from here, you can see that we're pretty much in the clear, because pi inverse of FA and Q, as I wrote above, is exactly equal to this intersection, GI1, GI2, up to GIK. And so if what I have on the left is not fully contained in pi inverse of FA hat, then it certainly cannot be contained in every single one of these. So hence, there exists some index, IL, for which pi inverse of YB hat intersect Q is not fully contained in this GIL. And just flipping back, you'll note that this is exactly condition 2. So this is condition 2. And of course, since pi inverse of FA hat is contained in every single one of the GIs, is equal to the intersection of the GIs, this means that pi inverse of FA hat is contained in this GIL that we found. And this is condition 1. Let me flip back so we can see that. This is exactly condition 1. So that means that A and B are indeed in one of these coverings. So A hat, B hat. So we conclude exactly what we wanted. A hat, B hat is indeed an element of our, one of the G's that we found. We called it IL. And hence, D of n is indeed covered by RG1 up to RGR. Hence, we have shown that the size of an extended formulation is an upper bound to the size of a covering. In the next lecture, we're going to show that any valid covering has to have exponential size. And this is going to conclude the result that we want, that the extension complexity of the correlation polytope is going to be at least 1.5 to the n. We'll pick it up next time.